Hi, I'm back with a new tutorial, and this one is going to be all about simulating different tools and their effect on any kind of material actually. So it can be a CNC mill drill bit, it can be a chisel and a hammer, it doesn't matter. We're going to see how we can actually simulate its effect and the aesthetics that using different tools creates. And the reason why we are going to be doing this is because during the autumn semester, I'm going to be working with this bad boy right here, a big robot, and we're going to be attaching this kind of a hot knife, a similar one to this, to the robot arm, and it's going to be kind of used to cut out styrofoam, right? Carve out styrofoam rather. And quite a lot of aesthetics will come from the tool that we use, right? Like the surface finish will be dictated by the tool that we are going to be using. And I want to actually see what kind of surface finish we're going to get before we're going to be doing the cutting. So I want to simulate it. I want to simulate the subtraction, right? So you might be thinking, well, just do Boolean difference, right? Just keep removing it, do some sort of a loop and do Boolean difference. That's too heavy and it breaks and it doesn't work, right? Would be a very, very simple tutorial, but unfortunately it doesn't work that way. So instead I'm going to show you a very basic setup first, and then we're going to kind of increase the complexity and the visual interest of it a little bit further. So the basic idea is that in Rhino, I'm going to draw out my styrofoam sheet, you know, the bulk material that I'm going to use, and I'm just going to use a box for it. A box that is 300 millimeters by 300 millimeters by 100 millimeters in height. Something like that. Let's go for shaded view. That's our box, right? And just like any good sculptor, you need to visualize. You need to visualize the object that is trapped inside of the material, right? So we're going to, I guess we can just draw out a surface in the bottom, like that. So there's just a, where is it? There we go. There's just a surface here. I'm just going to move it up. Doesn't really matter where, somewhere inside of this box thingy, right? Inside of my material. And just to make it a little bit more interesting, I'm going to rebuild the surface. Let's say 4 by 4 points, degree 3 by 3, right? Hit OK, hit F10 to get the control points. You can't really see the control points, so I'll switch this to wireframe view, or we can go for ghosted view mode. And I'm just going to create some sort of a, I don't know, let's do a booby. So I'm just going to take the middle points here, like that, and just lift them up, like so. You know, just a hill. Nothing too fancy. Okay, so we have a surface, right? And basically this surface will dictate how the styrofoam box needs to be cut, right? So the cuts are going to be made until the drill bit reaches the surface. And I probably should tell you that we are going to be, right now we're going to be simulating just a drill bit, a CNC drill bit carving out the top, right? So something very, very simple to understand. Right, so now it's time to reference in our geometries. So I'm going to create a surface component right here, set one surface, perfect, and a brep component, set one brep. Click on the box, perfect, right? So our box is a boundary representation. That's because it's a poly surface. And our guiding surface for the tool path is just a regular surface, doesn't matter, right? So we have two of these. All right. So now, actually, I kind of want to name them, right? So brep, I'll just select it, click the scroll wheel, and choose to group it. And then I'll right click on the group and name the group, I don't know, stock material, right? That's our stock material. And for the surface, I'm gonna group it as well and call it cut surface, I guess, something like that. Very, very simplistic. Oh, and you guys really like when I do this bifocals. This will just doesn't really show up, does it? Do I need to enable it? Wait. No, it works. Okay, never mind. So bifocals will just show you what kind of tools I'm using. So cut surface, stock material, right? So right now I just want to hide everything in Rhino just so that it's not in the way. And I will hide the stock material for a bit and only work with the cut surface right now. So first things first, we want to decide what kind of a drill bit are we going to be using, right? What kind of a cutting object are we going to be using? So it's going to be cylindrical, duh. And it can be rounded, but in this case, I'm just going to make it kind of sharp, right? So it's just going to be a cylinder. And you can either draw it, and I would prefer to draw it, honestly, or you can describe it in Grasshopper. Here, I'm just going to model it out, because why not, right? So I'll start, I'm going to make a cylinder, start at 0, and the diameter of the cylinder is going to be, let's do 1 centimeter. For 30 millimeter, yeah, sure, let's do 1 centimeter, why not? Like that. And then the height, let's do 10 centimeters. Oops, 10. Well, 10 is a bit long, isn't it? Maybe we can get away with 50? Yeah, let's do 70. So 7 centimeters height, 1 centimeter in the diameter drill bit, right? That is our cylinder. And notice how I am drawing it at x, y, 0, 0, 0 coordinates, right? I'm centering it right here. That's because it's going to make it so that moving it to the correct positions is going to be very easy because it's right at the origin, right? So the movement is going to be simple. So keep in mind, like have your drill bit centered. And I'm just going to reference it as a brep, like that. Set one brep, our little cylinder right here. Group it, call it cutter. There we go. That's our little group right here. So now I want, and for now let's just hide the cutter. So now what I want is I want a path for this cylinder to go along, right? And that path needs to kind of follow along the surface. So I can either start kind of creating a spiralized pathway or any kind of parallel pathway or something like that. But for this particular example, I don't think we really need to. Instead, I am just going to contour the cut surface. So I'm going to do a contour. So the cut surface is going to be the one that's contoured, right? So that's the S input for the shape. Then the plane, or sorry, the point from which it's being contoured is indeed 0, 0, 0. That's fine. So this is just from where will the contours be calculated. Then we have the direction. So the direction can be, not can be, but should be either X or Y. I wouldn't trust with Z in this case. So let's do Y. Direction doesn't really matter. Direction Y. Wait, is that is not, yeah, that is the direction. And then distance between contours, right? So keep in mind, our cutter is 1 centimeter in diameter, right? So if our cutters, if our contours are 2 centimeters apart, that means there are going to be ridges between between the cut paths, right? It's not going to eat up all of the material. I can actually show this. So let's create a slider instead of a static number. I'm going to create a slider between, let's say, 5 millimeters, dot, and 25 millimeters. Enter, right? So the shortcut for creating a slider is 5 dot 20, minimum dot maximum number, 525. I'll just connect it here. So now it's making contours every 5 millimeters. And if I increase it, this is every 25 millimeters. Right? So I'm going to be using this for now, just to show you that, ridges will indeed appear. Now, what we want to do is on these contours, we want to place this cutter at every 10 millimeters. Well, not necessarily 10. I would probably do every 5 millimeters, right? We want to place a cylinder so that we are kind of recording every position of the drill bit, right? Along all of these paths. So I am going to take these contours and I'm going to say divide length. Rather than just divide curve, I'm going to say divide length, like that. And for the length, I am going to use the radius of my cutter, right? So I'm going to say, in this case, 5 millimeters. Bam, like that. So now it creates points, and the gap between each point is 5, right? And that's basically it. At this point, I can just straight up move the cutters, the drill bit geometry. I can move it to every one of these points. And so points are, first I'm going to do it and then I'm going to explain why this works, right? So you can see that I directly plug in points to the translation or motion input here, and they are actually placed in the correct position. Why does this work? Why do you not need a vector? Well, that's because our cutter is located on the 0, 0, 0, right? And each of these points, if I actually look at what kind of information I have here as a panel, through a panel, I guess, each of these points have 3 coordinates, and those 3 coordinates can be read as a point or as a vector, right? And if I use these coordinates as a vector and I'm moving from 0, 0, 0, that means it's just straight up going to show me the correct position. Or not show me, but use the correct position for the points. Well, that was a shitty explanation. Alternative to this would be for me to create an XY plane, right? So that's my starting point, right? Or to construct a point, there we go, right? So I have this starting position and then create a vector between 2 points, right? So I don't really need a plane. So create a vector from the starting point until every single one of these points, right? These vectors. And if I visualize them, vector store display. There we go. Anchor, vector. If I visualize them, this is how they look like, right? A crap ton of vectors. So now let's look at, this is the original points and their coordinates. Copy, paste, and let's look at the vectors and compare them. Notice any similarities? These are two exact same lists, right? So incidentally, we're not doing anything with these two nodes, right? We can just straight up plug in the points to the translation and read them as vectors. Okay, so that's that. You can see how many B-reps we get, and actually the movement of them doesn't take that long, but you notice that my computer lagged out as I plugged in the B-reps. That's just simply because it creates 803 cylinders, which are polysurfaces, and that's heavy on the machine. So what I'm going to do is I'll convert these B-reps into meshes first, or this B-rep, this cutter B-rep, into a mesh first. So I'm going to use mesh B-rep component, like so. And let's take a look. This actually looks pretty good already. It's 92 faces. What if we use, for the settings input of the mesh B-rep component, what if we use speed settings? Settings speed. That doesn't really change anything, does it? No, it doesn't. Anyway, so we're just going to straight up use the mesh B-rep with default settings. And now I'm going to connect it like so, and then this becomes faster, and also the graphics card is not complaining that much. So this is just like a visual optimization thing. Okay, we're slowly moving forward. Let me just group that. Group that. I'm just making it a little bit more tidy. Perfect. Perfect. Okay. So now actually what I want to do is use these tools. I don't care about the surface anymore, by the way, because I have the tools here, right? Not the tools, but the cutter placed on each of these points, right? So I am going to remove from the stock material with these cutters, right? And see what's left. So this is where I said that you could use Boolean difference, right? Remember? But it would, trust me, it will crash. If it won't crash, it will create undesired results. It will make a mistake somewhere. So instead we're going to use voxels, because that's much, much faster. And for voxels, we always use Dendro, because, I don't know, it seems like the most stable plugin out there for voxels. So I'm using Dendro, and I'm going to, first of all, convert all of my drill bits here, or drill bit positions here. I'm going to convert them into a volume, a Dendro volume, a voxelized volume. So first things first, actually, here we have a crap ton of meshes. I'm going to right click on the move output, G output, right click on it and choose flatten. That's graphed. Choose flatten. There we go. So now all of my meshes are placed into one big happy family, right? In one list. And since they are right now placed in one list and not separate lists, by the way, they were placed in separate lists because notice these rows? Each row was a separate list of meshes, right? So by using flatten, we just said, no, all of them come in all at once, right? And since they are coming in all at once, I can use mesh join on them, and all of them are going to join up into one single mesh. That is 74,000 faces. That's not too much. That's fine. Okay, so now I have my single mesh here, and now I'm going to convert it into a dendro volume. So I'm going to go to convert, and I'll choose mesh to volume, like that. I'll connect my mesh join to the mesh input here, and for the settings input, I'll go to convert tab again under dendro and choose create settings, like that. Settings connect to settings, and never do this, by the way. You should never do this. Disconnect. First, before you connect the settings, you need to specify the voxel size, or else by default the voxel size is 1 millimeter, and thank God that we're using a small, 300 by 300 millimeter block. If it was a bigger one, this would just straight up crash immediately. So voxel size 1, nah. For now, let's do voxel size like 5, and then we're going to kind of keep dropping it down in size. Lower the size, higher the precision, right? So for now, voxel size 5. For other inputs, bandwidth, ISO value, and I believe adaptivity. Yeah, adaptivity. I wouldn't change these. Especially adaptivity, because adaptivity is pretty great at reducing amount of polygons. ISO value, 0 will try to keep it as true as possible to the original size. If you mess around with the ISO value, you're basically creating this kind of an offset effect of your mesh, which sometimes is useful, but not in this case. And then for the bandwidth, I have no idea what bandwidth is, so so let's create some settings, connect that, and that's it. Now this mesh has become a dendro volume, and I can actually let's actually hide most of it, right? Because here we have our mesh to volume, right? So this is the dendro volume, and I can convert it back into a mesh, and we can just investigate and look at it, how it works, right? So let me convert volume to mesh, like that. And it's going to ask me for settings, and we already have the settings, so I'm going to use the same ones. Bam. Just like that, and let's use some custom preview to showcase it a little bit better. And that is our mesh. Easy, right? Easy peasy. So now for this mesh, let me just show you the voxel size. If I decrease this to 2 millimeters rather than 5, enter, it breaks. It gives me an invalid mesh. So dendro, this actually is a good segue. Dendro is not that stable, right? It tends to break quite often, and only like certain values work. So you can see 3 millimeters works, 2 millimeters didn't work, 1 millimeter might work, might not work, who knows, doesn't work. So I'm going to actually use 2 millimeters here, and I'm going to see how I can make this invalid mesh into a valid one, right? So first things first, and by the way, I know that it's an invalid mesh by hovering over the output and seeing that one locally defined value and it says invalid mesh, right? I can also use a panel to see that, right? So usually invalid meshes are created when you have too many, not too many, but when you have vertices or points in the mesh that are not being used by any of the faces of the mesh. So a bunch of junk, right? And dendro likes to create that kind of junk. So there are two tools that kind of deal with it. First one is by Daniel Piker, and it's in Kangaroo 2, and it's called Combine and Clean. Combine and Clean. This one right here. And doesn't work, didn't help me at all, right? It's still an invalid mesh, so I can't use that. So instead we use the second one, and the second tool is located in the pufferfish plugin, which is, you should have it. If you don't have it, get it. It's in the foodforrhino.com. You can download it. So pufferfish, under mesh, there is rebuild mesh, this one right here, rebuild mesh, where you just plug in your mesh and you use toggles, Boolean toggle to choose what you want to do with that mesh. So first one is rebuild normal, second one is cull unused, third one is unify normals, and so on. And it has pretty good document or explanation of what each of these inputs does when you hover your mouse over it. So in our case, we want to use cull unused. I will just switch toggle to true, connect it to cull unused input here to true. And now as I'm looking at it, it's instead of invalid mesh, it says, you know, mesh with this amount of points or vertices and this amount of faces. And now I can connect it to the geometry preview right here. Perfect. We solved it. Yay, we got rid of the trash. So this is with voxel size of 2. Let's switch it to 1 millimeter. And this is voxel size of 1, right? Nothing too fancy, you know, a pretty simple geometry. I can even increase the length between the cylinders, the gap between the cylinders even further. Instead of 5 millimeters, what if we use 10? Right? So you can see how the voxels connect, right? And you get this kind of a ugly effect. So I'm going to be using something like 7. It needs to be dense enough, right? This seems to be good enough. And then for the gap between these, oh right, I wanted to show you what happens if the gap is not close enough. So this is what's gonna happen, right? Let's do that Boolean difference operation, right? So without actually doing Boolean difference. So we have our volume right here of these cylinders, right? Joined up volume. And we can create a volume from the stock material. So I'm just going to simply do that. Volume, was it mesh to volume, something like that? Oh, come on, mesh to volume. Yeah, there we go, mesh to volume. Connect stock material to mesh to volume input, M input, use the same settings for it. You can see that, you know, a volume is created for it. And now we have 2 volumes basically. Let me get rid of the preview so that you can see better. This volume right here and this volume right here. And we can use those 2 volumes to subtract from this one with this one, right? So let's go to dendro, intersect, volume difference. That's, you know, like the Boolean operation that I keep talking about, volume difference. We subtract from this one with this one. Bam. We end up having this kind of geometry, right? And then we will be using our volume to mesh to create a mesh from this geometry. And now we can actually use custom preview. There we go. A little bit on the ugly side. Maybe this is better. So if I zoom in, you can actually see, you know, the the drill path, right? So now, what happens if instead of 25 millimeters between every contour, what happens if we use 15 millimeters? Of course, it's gonna become much heavier, so just give it some time. This is how it looks like with 15. There's still gaps, but the gaps became smaller. So what happens if we use, let's say, 7? You know, same as the divide length. Same thing here. 7 millimeters between the contours. Voila. Of course, there's kind of crap on the ends here, but that's fine. We can remove that crap later. Seems to work just fine, and we end up getting that kind of sweet simulation of the surface. So that's the basics of it, right? By the way, you remove this by just shrinking the box a bit before the simulation starts. As easy as that. Or enlarging the box before you create the cut surface. So actually, let me do that. Show selected. Where's that surface? There it is. That surface, if I just scale it up 1.01, like if I scale it up 1%, or let's do 2%, 1.02 in all directions. And then we wait for this to stop having a heart attack. There we go. Everything's fixed. We have a clean little pillow that's simulated. Congratulations. We have ourselves a toolpath simulator. That is not that heavy, honestly, right? So now I want to do something a little bit more fun, a little bit more interesting, visually interesting. So let's talk about chisels, right? And let's talk about actually creating not G code, but instructions for the machine that generate a little bit more unexpected results, a little bit less machinic results. So I will begin by showing you what I mean by saying chisel, right? This is a chisel, right? And we are not talking about these kind of chisels right here, not the flat ones. We're talking about the wood carving chisels, right? This thing right here. Notice the arc that they make. So what if we can use that chisel and simulate how a wood carver goes in and then goes out, right? He makes this kind of a, he or she makes this kind of a arc, right? So can we simulate that kind of an arc happening and being used as a carving method for our geometry right here? I think we can. So let's do that. So our cutter is not going to be, and actually I'm going to do another definition. So this one is, let's say, done, right? This one is done. And I'm going to do another one, right? Let us disable that. Actually, let me disable all of it like that. Perfect. By the way, these files available for Patreon supporters, blah, blah, blah. If you're lazy, if you don't want to follow along and just want to get the file, consider supporting me on Patreon. Sell out. Anyway, we are simulating instead of a drill bit, we're simulating the chisel, right? We're not just simulating a chisel at one position. The drill bit is easy to kind of define because it's just spinning, right? The chisel is moving. So we want to have this kind of a geometry for the chisel that has a start, a middle point, and the end. And it's basically this kind of an arc, of going into the material and then going out. Very hard to explain without actually drawing it. So I'm going to draw it and hopefully you catch my drift. I'm going to draw out how is this called? I'm going to draw out the arc that the chisel makes. Basically, this arc right here. So let's start at 0. And I'm going to go down. Right now, this is not going to be at scale. So I'm just going to go down by 10. I'm going to go to the side by 50. Hello? 50. Yeah. And then I'm going to go up by 10. This is not, don't worry about it. So I have this curve. All I care about is just the control points, right? So I take the middle control points or the bottom control points, and I'll just scale them down to something like so, maybe. Yeah, looks better, right? And now I'm going to take this and I'm going to scale it to the correct size of how big I imagine the chisel is going to be. How big is the chisel going to be? I would say 3 centimeters, something like that. Let's actually use 5 centimeters for now, just so that we don't need to do a lot of carves to actually get the wood out, or not the wood, in this case styrofoam out. Let's just use a big one, but we can scale it down anytime we want. So we have this, and now comes the tricky bit. I'm going to take it and I'm going to move it from its middle point to the 0 position right here. Zoom selected, something like that. And I'm going to rotate it, rotate 3D. I'm going to rotate it around the x-axis upwards, right? So that it's just looking upwards. Something like that. Okay. And now, I really want this to be a little bit higher. So I'm going to lift up these 2 endpoints by 5 millimeters up. A little bit more aggressive. And as I was lifting those 2 points up, you can see that the bottom got lifted up. I can't have that. I must have the bottom, the midpoint, right at the 0, 0, 0 coordinates. So I need to move this back to 0, 0, 0. Just like that. Perfect. Okay. So we have that. And now I'm going to add 2 more vertical lines here. And I'm going to close it off. So I'm basically making an enclosed polyline, right? Let's go to the front view, like that. Perfect. And the length of a chisel, I don't know. Let's do something. Actually, it's not the actual length of the chisel, so we don't need it to be precise. So let's do 70 millimeters, something like that. 70, then the width was 50, right? And then it goes back down. Now we join it up. Perfect. And we have ourselves one of the cross sections of the chisel as it's going in, right? So this is by no means, this is not me drawing out the chisel. This is me drawing out the cross section that the chisel makes. God damn it, this is a tricky one, Okay. But hopefully, as you're following along, you will understand what I mean by that as we're going to be progressing through this tutorial. So I'm going to take this cross section right now, because this is like the deepest cut that it makes, but it needs to make this arc, right? This arc. So I'm going to take this cross section. I'm going to move it to the side. I should probably move it by some fixed amount. Yeah, let's do that. I'm going to move it to the side by minus, I don't know, 70. That's too much. Minus 50. And when I say move, I mean copy, not move. So now I have this gap of 50, and I'm going to take this and probably just rotate 3D. I'm going to rotate this around this axis by, let's say the starting attack angle is 30 degrees. 30 degrees like that. And move it up by another 50, maybe. Yeah, 40, 50, something like that. So this is like the starting position. All I care about, by the way, are these arcs. Everything else is just for me to make sure that it's going to be a solid shape once it's done. Once I've finished with the lofting and so on. So all I care about is this. So the chisel starts at this angle and it's going to go here where it's basically all flat, and then it's going to go out again where it's not flat anymore, where it's again at an angle, right? You're lifting it up. This is not how any of this works, but hey, whatever works, right? So I'm just going to make a mirror here, like that. And once we have 3 positions, I can loft between them. Just make sure that your seam of the loft is is correctly placed. So you just move the seam points around, enter, hit OK, and then just cap. Select the poly surface and hit cap. And now you have yourselves negative space that a chisel creates. That's the easiest way of explaining it. I'm going to reference it in as a brep, right click, set one brep, like that. The attack angle is pretty heavy here, but maybe it's gonna work out, we'll see. We have ourselves a brep, and I'm going to call it, group it and call it chisel carve space, or yeah, carve negative space. That's a mouthful, but it is what it is. Chisel carve negative space. Then we still have show selected. We still have this box right here, which is our actually, can I just borrow it from here? Will be faster. I'm just gonna borrow the cut surface as well as the stock material. Copy, paste, Control C, Control V, enable, there we go. We have our surface and our brep. The surface is, let's group it and let's call it the cutting surface. And the brep is, of course, our stock material. There we go. We're back at square one, but now with a fancier tool that will require us to kind of rethink the whole approach here. So I think so when I started talking about this, I talked about the contouring and the drill bit and so on being very machinic and not the tool itself not creating any kind of aesthetic effect, but rather just being, you know, as CAD as it can get, right? In this case, I do want the chisel to create some sort of a texture, some sort of a little bit of an unexpected texture, maybe even random texture, right, on the surface. So we are going to be using, rather than contouring it, we're going to be using some random population of points. So as per usual, we start with the cutting surface. So I'm gonna hide everything else, and I'm just going to populate geometry, and I'm just going to populate like sure, 100 points. Let's do 50 points for now. 50 points, right, on this populate geometry. So 50 points on the surface. So these are the points which are going to be evaluated as the robot is carving into our stock material, right? So we need to move our geometry, our chisel carve geometry, to those points. Again, a very simple procedure, just like that. And as per usual, we need to convert the chisel geometry into a mesh just because it's going to be faster. You will notice that the angle of attack is always the same and everything is the same. We can control this later. For now, we just need to make this work. So first of all, I'm going to make the brep into a mesh. Mesh brep. Like that. I'm repeating the same step as I did here. Mesh brep, and now we connect it, and now it's much faster. And we will mesh join all of those up, and use, we don't actually need to use anything, just to make sure that everything joins up. Right now we don't need to do it, but just in case, I'm going to right click on the move G output and choose to flatten it again, as I did before. Okay, so we have all of our negative spaces joined up into one big happy family, and I can actually, I'm going to really quickly do this. I already explained this part, so I'm going to do this real fast. It's basically the same procedure as what we did before. So, but next steps are going to be a bit different. So, mesh to volume. We need 2 of those. Create settings. We need 1 of those. 1 millimeter for the size of the voxels. This becomes a volume. Wait for it to calculate, perfect. And then stock material becomes a volume. That went much faster. And then we do volume difference. We remove from the stock material, so that's A input with the chisel negative space volume, that's B, then volume to mesh, perfect, settings are created, cast your votes if this is an invalid mesh. And it indeed is an invalid mesh, so we just use mesh rebuild or rebuild mesh component on it. We toggle to remove the to cull the unused vertices. We custom preview it. Oh wait, no, never mind. This should work. I wonder why it's not. Oh, it is showing up. And we disable preview of everything except the final one, and this is what we get. Right? So even without any rotations, I feel like this is pretty cool, right? A pretty cool effect, right? To have, and doesn't look that machine made. So now let's see how we can make this nicer. So first thing is I'm going to show selected. Where's my tool? There it is. And I'm going to scale it around, scale this object, enter, around, so the base point is going to be 0, of course, and I'm going to scale it by 0.5, by half, like that. See? And now, since I've done that, 50 points are not nearly as enough, right? So I need to increase the count to, let's do 100, but I think we will need like at least 300 points here to work. There we go. So that's pretty neat, isn't it? Right? So now we can use any kind of surface as our cutting surface, and it's going to carve out, or we're going to simulate how using a different kind of chisel is going to, what kind of effect is going to have. And in this case, everything is like all of these moved meshes are aligned with each other, but I can as easily just rotate object or rotate 3D, doesn't matter. Let's just use rotate 3D. So I can rotate each one of these around the populi geometry, around each point with random value. Just keep in mind that you need to choose degrees, not radians. Random value. And the question is, actually, let's make some gap here. That's rotation, that's movement, that's random. There we go. That's going to be a little bit easier to see. So the question is, how many random values do I want, and what's the range, right? So the range is going to be, let's say, between dash dash, or not dash, slash slash, minus, let's say minus 30 degrees to 30 degrees. That's the rotation scope. So, it's going to get numbers somewhere in between these two. And then for the number of random values, that's the number of how many points we're generating, and that is controlled through this slider. So I'm just connecting the slider to the random n input. And now you can see that each of these are being randomly rotated, and I can use, instead of using the original one, I can use the rotated ones. And let's do it this way. I'm going to disable the preview of this and just kind of switch the wires up so that you can see that as I'm switching the wires, this is going to change to something that's a little bit more chaotic. Yeah, you can't really see it, can you? But it did work, I promise. It did work. It is indeed a little bit more chaotic. I can switch back just so that you can see, better. So here it's almost like this Voronoi effect, and here everything is a little bit more aligned with the Y direction. Yeah, with the Y direction, because all of our chisel paths are oriented along the Y direction. All right, so we do keep the randomized rotation. There's also options for, instead of having the chisel always come in from the top to bottom, right? There's also an option for the chisel to attack it at a perpendicular angle of the surface. But I think we will use that in a separate tutorial. Because I still need to figure out ways of how to avoid collisions in that regard. But this is basically it. So let's actually change the voxel size to 0.5 just to see if it's gonna crash or not. Always fun. And then if this works, I'm going to finish up with one last example. And that example, I'm not going to explain it too much because that's going to be in future tutorials for sure. But it's going to be something that's going to be, at least visually pretty interesting. So this is with quite high resolution. And you can see that we still need to have more points with this size of chisel, but already here, this looks pretty sweet. And you can actually, oh, come on. I don't know why Grasshopper keeps hiding itself. You can actually bake this out like that. You know, and actually use it in your Rhino files as some sort of a paneling system. You know, just don't forget to rotate it and whatnot. Come on, rotate, rotate. It's not lagging, it's just me being stupid. Okay, so that's that, and then we change this to Arctic view. That's how it looks like. Boobies. Anyway, let me save this so that I can distribute it later. That's the 13th tutorial. Great. And this one as well. And I'm going to open up another file in just a second. Okay, there we go. So this is my work in progress file, so to say, preparation for future tutorials and whatnot in the coming semester. And this is just to show how I'm using the stuff that I've just taught you, how I'm using that in the grand scheme of things, so to say. So this is just going to be an overview rather than a continuation of the tutorial. I will be uploading this file as well for my Patreon supporters, by the way, just so you know. So basically, a little bit more of a complex shape, nothing too fancy, is created here, right? And it's driven by like these two sets of curves and two attractor curves right here. If you want, you can just pause the video at certain moments and just kind of follow along and just copy this whole thing if you want to create something similar to this. Almost that part as well, and the end. Okay, so this wall or whatever it is, this pattern is being selected, is being baked out and treated in Rhino to create these kind of 30 by 30 by 10 centimeter sections, or 300 by 300 by 100 millimeter sections, these parts, right? And all of these elements, like these separate elements, now can be manufactured or can be produced out of styrofoam, right? Because they fit in the stock that we have. So that's this bottom part. The top part is me getting one of these elements out. So let me show you that, or actually let me show you all of it. So getting one of these elements out and about, disable that, and extracting only the surfaces that I'm going to be cutting of that element. So let me hide this so that it's not in the way. So I'm only extracting the surfaces that are going to be cut in the box. Sorry, into the stock, right? Then these surfaces are being populated with points. You already saw that. Planes are created on them, and basically blah, 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 a lot of stuff happens. It's going to be shown in future tutorials, and by the end of it, we have a robotic manufacturing simulation at our hands. which apparently is going to take 172 minutes to complete, but that is it would be much faster. Never mind. So the simulation actually looks pretty neat. So you have your stock material here, right? That is show selected. This one, wire, extract wireframe, lock, hide. There we go. So now you can see the stock material here. And as I'm moving forward at the time, you can see that the tool that is right now just a rectangle, the tool that is doing its magic, right? And going through this whole space, right? And unfortunately, there's no way for us to see, how would this kind of tool carve out this kind of material up until now. With my tutorial, we can do it, right? So where is it? There it is. So here we have all of the joined up angles of the tool. We are creating the mesh, we're getting the volume difference, the same thing that I've already shown. We're creating the mesh from volume and rebuilding the mesh, right? And if I bake this out into the default layer and just drag it right here, drum roll please, Arctic view, that is how it looks. That is how it would look like being cut with a rectangular knife, rectangular cutting tool. Remember where was it? Hot wire cutting knife that I showed at the start of the tutorial? So that, right? And if we ran this through all of these segments, we could replace all of them and then see exactly how this will work. And actually, I'm kind of curious. What if I rotate this, get a bounding box in here, like that? I want to place the, oops, too many copies. I want to find which element I'm actually using of the wall and replace it with the carved one. Okay, that's not gonna, no. Yes, this one. There we go. So instead of this one, we're going to take this, get that backside endpoint right there, anchor it to right here. Perfect, delete that. And you can see now this element in place. Let's go for Arctic view. Pretty neat, huh? Oh, it's chewing out quite a bit. I'll need to fix that. It's chewing too much. But other than that, I think that this is much more, it's nice. It's just nice. So this is going to be a bunch of additional tutorials in the future. Let me save that, upload that to my subscribers and or supporters, and let's call it a day. So I hope you've learned something new with this one. I'll see you next time. Bye.